Hello everyone and welcome to the 15th lecture of remote sensing course. In this course we are going to discuss three techniques, mainly spatial filtering, band ratioing and principal component analysis techniques. We will also try to cover the decorrelation stretch, which is an offshoot of principal component analysis technique. There are three techniques mentioned here. The first one is on the individual channel or bands, and the second band ratio and principal component analysis techniques are performed on multiple bands, means that is a single and this is multivariate analysis. So let's see that what basically spatial filtering means here. Basically the purpose of spatial filtering technique is to improve the again image quality, so that interpretation becomes much easier or even classification becomes much better or accurate. And the concept of spatial filtering basically came from the this electrical or electronics engineering, where they used to have a kind of single dimensional or a slit kind of filtering to pass the signal, certain type of signals, and certain to block certain types of signals or noises. So instead of having just one dimensional, here in digital image processing we employ two dimensional filters, and it is also called convolution filtering techniques. Basically there are major, if we see the types of these two techniques, then one is the low pass filtering technique, which emphasizes the regional spatial trends or de-emphasize the local variability. So that is why it is called low pass filter, whereas high pass filter emphasizes the local spatial variability, and they are just opposite in that sense. And edge enhancement combines both filters to sharpen edges in the images. So edge enhancement is a kind of high pass filter in that sense. As I was mentioning that if we see this waveform, and here what we find that here is a combined effect, and various signals are together, but these signals through filtering, like in electronics engineering people do, can be separated out, and different wavelength signals can be seen. But this is single dimensional thing. In spatial filtering, what we try to use a two dimensional matrix, a convolutional filter, and then try to move throughout the image and try to improve the image as per our requirements. So if we see this first, the low pass filter, that is convolution matrix over this, the size of this moving filter or moving matrix may vary, but it has to be a odd number. Here it is like in this particular example, it is a 3 by 3 matrix. We can have even 5 by 5, 7 by 7, 9 by 9, but the larger the size is going to be this convolution matrix or a spatial filter, more the time it would take, more the regional data, means more surrounding or neighboring pixel values will come in calculation, and therefore that may not be very efficient. So initially we can think as a 3 by 3 filter, and as the purpose of low pass filter is to de-emphasize the local variations which are present in an image, and in reverse we get the emphasis on the regional variations. So that is why it is called low pass filter. Now if we see, this is the original image, digital representation of this image is also shown here, and when it is subjected to this kind of filtering, then this is how the calculation is done. So either we can have this kind of thing or having a one integer, and this is a low pass filter. What it is doing basically, as you can see, that it is making the average of all surrounding 9 pixels and giving the centered value, where like here an average value. So instead of like here value 30 in original image, that gets 27. Likewise the value here 26, it gets 25. So that, as you may realize, that the difference here between 30 and 26 was 4. After spatial filtering, low pass filtering, the difference became only 2. That means the local variations has got de-emphasized whereas the regional variations are have become obvious. As you can see that the lot of variations which were present in the image, especially in the built up areas and other part of this image, they have all disappeared, and now we see a more regional picture. Though the sharpness of image has also, this is a kind of diffusion filter. So this is how it can be done. Now it is not necessary that all these values should be 1. We can change these values as per our requirements, but that is mainly done in case of directional filters, which we will see little later. And this kind of filtering is very helpful in the mapping, where we do not want to see lot of details, local details. We would like to see the regional details, and therefore we apply a low pass filter. There are several high pass filters can be designed like this. As a few examples, 6 examples are shown here, that convolution matrix for edge detection, directional particular direction, or high pass filtering can be achieved by subtracting result of a low pass convolution from original image. And this is by devising matrices based on more complex algorithm like B and C. Edge enhancement matrices are there, which can be add edge to the, these are the directional filters, as you can realize, and that in certain directions things will. So we will see some examples here. A high pass filter in which the convolution matrix is 11 by 11 pixels. So as I was mentioning, this odd number 3 by 3, 5 by 5, 7 by 7, 9 by 9, even 11, and see this all local variations through this high pass filter. It is not directional, just simple high pass filter of having a size of 11 pixel by 11 pixels have completely evaporated the regional variations, but however it has brought the local variations, has emphasized the local. And then if somebody is looking for some linear features, maybe linear mapping or for road mapping or any other such features, then this kind of filtering can be very helpful. All these gray shades and everything has almost disappeared, and image has become virtually a binary kind of image, but your interpretation on linear features or some other features which are having very contrasting surroundings in original image can be emphasized very clearly. Similarly, if we bring the direction, instead of having in all directions the same, like in case of high pass filters here, that like if I take this example, then -1, -1, minus. So in all 4 directions the treatment would be same. That means the values from the surrounding pixels will be treated same. But in case of directional filters, as you can realize, this example is again from 3 by 3 convolution matrix, is that only on one direction we are using minus values, whereas in opposite, in the northern part, we are using the positive values. So what this do, A will produce the image in northward direction, which will emphasize the features if there are shadows, and in northward direction they will be emphasized, and B will produce altogether a little different results, and it will produce a southwestward direction. So remember that wherever you are having minus values in opposite direction, the emphasis would be there. Here we are having minus values in southern side, so we will have northward direction things. And this is then an example that different directional filtering. The image was the same, filtering is done earlier, it was simple high pass, now directional. The appearance would be different, and linear features or which are perpendicular to this traverse direction can be emphasized very easily without much human interventions, and then mapping of such things can be done very easily. So that is the advantage of having high pass filter, especially with some emphasis on certain directions. Now in this example, in the B example, we are having southward emphasis, we can have just opposite. So not westward emphasis, we can also change these values put here. So then we will have this northwest, southeast, in all directions such filtering can be designed and results can be obtained. Now we go for the multivariate image analysis, and the spatial filtering, as mentioned earlier, is always done on the single band, then later on you can combine. Even sometimes people also apply these edge enhancement or filtering techniques on a false color composite as well. So what it would do, if it is not very strong filter, what it will do, it will produce an image output which would be little sharper maybe compared to the original one. So in order to sharpen image, we use this high pass filtering. In order to de-emphasize or make more smooth appearance, a diffuse kind of image, we use the low pass filtering. In various image processing softwares or even photo editing softwares, you may find certain options like diffusing the image or sharpening the image. So edge enhancement or in particular direction can be done, and so on. Now in multivariate image statistics, basically, as you know that in remote sensing, instead of one band, we are generally having multispectral bands. Several channels are now available, and how to involve many channels in analysis. Just depending on 3 channels for false color composites and doing everything on false color composite we will not be utilizing the entire number of channels which are available. So the best thing is to get involved in this multivariate image statistics or analysis as we are concerned with the measurement how much radiant flux is reflected or emitted from an object is more than in one band, because a one band may have different reflection of the same object, whereas in another band different signatures. So we want to exploit many bands and use in the analysis so that we can produce better results, better classification results as well. So in multivariate statistical, we measure such as covariance and correlation among several bands to determine how measures covary. Basically the purpose here initially is to see how bands are correlated. If like in let me give you example, Landsat MSS, initially the band 1 and band 2 they were very highly correlated, because the responses of different objects or features which were present on the surface of the earth were showing almost same responses in the bands. So if the correlation is very high between 2 adjacent bands or any 2 bands, then we can choose either one to use in analysis. But if there is a lot of difference, then we can use both of them. So that for that purpose, this multivariate image statistical analysis is very important. Two popular techniques are there. One in band ratioing, principal component analysis, or there are more complex steps are there. Instead of just simple ratioing, we create some indices like normalized difference vegetation index or some other indices to use multi-band data and create some better output. So we will see that how these things can be done. Now in the band ratioing, ratio of 2 bands remove much of the effects of illumination in the analysis of spectral differences. If you are having too much shadow areas and bright areas and shadow areas, if you involve 2 bands and create a ratio, you would find that the shadow effects have reduced, and this is what it is, that solar illumination is here. We do not bother much about the scattering which is happening in this atmosphere, but if the structure is something like this, then this part of this hill is having more illumination, and whereas other part goes in shadow. And in 3 channels are shown here, examples of 3 channels in this view graph, and here the same thing is there, but they are all showing different signatures. So if we start looking values 46, 23, 23 for red, green and blue, whereas here because of more illuminations in this part and present of a different maybe rock type, all 3 channels are showing the same signatures. Whereas due to the shadow, here it has got 46, it is just showing just half say reflection, and this is here also roughly half of on this side. Now ultimately it is getting recorded only 5, 14 and 32. So if we perform bend ratioing involving two bends, what we would find that this effect of shadow, one surface is illuminated, another one is not illuminated or in shadow, this will remove, and this is possible because of composition difference between two geologic units. In this example here, limestone and red bed, and which is grey white, and in the RGB that is red green blue in the combination of 3:1, and the red bed which is in RGB 3:1 determines the ratio of any two bands, whereas the illumination determines the magnitude of digital numbers received by the satellite. So this is the advantage of having bands. Now we see then output. Here a blue radiation means band 1 shows the strong topographic. Because why strong topography is visible? Because of differences in illumination. It is a hilly terrain, rugged terrain, and when illumination is there, there will be some shadow in a hilly terrain, and that will show the depth perception as well. So if we want to de-emphasize the depth perception, then we need to involve some bend ratioing. So here in this example, bend ratioing of band 3/2 was done, and which removed the effects of topography, and as you can see that this unit, litho unit, which was basically getting the same signatures in band 1, but in the ratio of band 3 and 2, which has removed the topographic effects or different illuminations because of shadow in a rugged terrain, and we can now identify that it is a completely different rock unit. So that is the advantage of having bend ratioing. A single channel, no matter how many types of image enhancement or filtering we perform, but still we may not be able to discriminate between two different lithologies which we are present in this particular example. But if we involve the bend ratioing, then because of we could remove shadow effects, we could discriminate two major lithological units quite easily. Same might be in case of forest cover, or in two different land uses, or maybe in two soil types. So the similar techniques can be employed, but there are not really very sort of there is no straightforward rules are written that if you are having this problem, you take these two channels, make the bend ratio, and everything will be improved. Not at all. So it has to perform. It's a kind of hit and trial. So you perform, you take two bends, make the bend ratio, and see whether results are satisfying, serving your purpose or not. That is one limitation of these techniques. Similarly, if you are having too many bends, you can create a bend ratio of several bends, at least maybe 6, use them, and then later on you can make also color composites. Those will not be a standard false color composite, but anyway color composites can be used. So composites of bend ratios, like example here that these two other bend ratios, this is the bend of 5/2 and this is the bend 7/4 of an example of Landsat TM, and what we are finding that once when we combined in RGB fashion ratio of 3/2, ratio of 5/2, ratio of 7/4 in red, green, blue scheme, then just compare individual with individual ratio and this final color composite. It is really giving very good results. Even the variations within one litho units which we were seeing in single bend ratio example now have been emphasized here, and then you can imagine that what kind of better interpretations or classification can then be performed on such color composites. Though these are not standard color composites, but when somebody is looking for mineral exploration or looking for different types of vegetation, different types of soils, different types of lithologies, then we need to try to involve as many as bends. Here bend 2, bend 3, bend 5, bend 4 and bend 7. So many bends have got involved, otherwise in a standard color composite you would be able to involve only 3 bends, and whereas here we are involving at least 5-6 bends. So 5 bends have been involved to create a color composite, otherwise only 3 can be used. So this example is from to find out the hydrothermally altered rock, and finally it was observed that band 5 is good for iron oxide detections. But again, if I apply the same band ratioing technique instead of in this area to another area, then the terrain conditions are going to be different, soil conditions, vegetation conditions, and I may not get the same result. So again, we have to see that which band will emphasize which kind of rocks or materials or alteration zones. Accordingly, we have to adopt these things. So there is no straightforward written rules that if you find this, follow this. No, you have to try different band combinations. Now a offshoot of his simple band ratioing is this normalized difference vegetation index, because they in a normal band ratioing there is no normalization, and therefore you get a very high value or very low value. But in this one you can normalize, like in this example, near infrared channel minus the red band divided by near infrared channel plus red band, and this used to basically for mapping or seeing the changes in the vegetation, that is normalized difference vegetation index, which is that we want to see the health of a vegetation. So by applying this kind of arithmetic on each pixel involving two bands, one near infrared, because near infrared band, as you know, the healthy vegetation will have the highest reflection, and a red one, which is if it is not that healthy, then it will have. So this will create a difference, and we can normalize it, and so whereas increases in red show stress vegetation and very near infrared shows the chlorophyll. So this way we can really map the health of vegetation even at global scale if we are using relatively low resolution, low spatial resolution data sets like NOAA AVHR, which is extensively used of using the time series data to see that how with global climate change, how the vegetation is changing and where it is changing maximum, where it is changing minimum. So that kind of analysis is possible involving two channels only, and but normalizing it so that we can emphasize that what is happening to the health of vegetation. How this works is very simple, as I have explained, that in near infrared a healthy vegetation will say roughly reflect in this particular example about 50% radiation, whereas in visible part of EM spectrum it might reflect only 8%. So if I use the same values and convert them to percentage, then this is what the NDVI is going to be 0.72 in this particular case when vegetation is healthy. Whereas in case of a vegetation which is say this is example, if I take a example of a deciduous trees, then before the fall of these leaves, when they become yellow, the infrared because of chlorophyll content has reduced, the reflection radiation back radiation of solar radiation may get reduced by 10%, whereas in visible part this may increase very significantly. So instead of in a healthy vegetation earlier, say for example it was 8%, now 30% is getting back to the satellite, and whereas in case of infrared it was 50%, now only 40% is getting replied, and therefore you see that the normalized difference vegetation index, that is NDVI, has reduced to 1.14. So from 0.72 it has reduced to 0.14. That means just looking the values or assigning some colors or a palette to these values on a map, we can see that where the vegetation is healthy, where is the vegetation is not healthy. The same technique is also used in agriculture practices or to assess the health of a crop in a region, in a area. If you are using high resolution images, then even at a level of a farm it can be assessed. So this is how estimations are done about the production of certain crops in different countries, including in India. Very extensively remote sensing is being used in India to assess that what kind of crop production is going to be in the say Kharif season or Rabi season. So the technique is very simple. You involve a normalized difference vegetation index NDVI. You use two channels, infrared channels and visible channel, and create this normalized index, and then you can assess this very nicely. This is the example of given of some parts of Europe and UK, United Kingdom and Ireland. And as you can see that in the month of June in 2003, the NDVI was something like this. The London is here, which is a completely built up area, less vegetation, that is why it is showing in really in a 0 or in minus values. Whereas average NDVI for here in October 2003, because this is a when you are having maximum greenness, maximum good growth of vegetation, and therefore you are seeing like this. But when it comes to October, just a fall period, then what you are seeing, a large area has become red. That means here the vegetation has changed. Or so that in this way we can assess that where impact of things are. This is of the same year, but if suppose this have been June 2072 and June 2016, then we can know that how things have changed. So if month is same, year are different, then we can see the changes which has occurred. We can involve time series data, how things have changed, where things have changed, and how much things have changed can also be estimated. So this is a very good technique involving minimum two channels and creating a indices. This is simply a offshoot of band ratioing. Now the another very popular technique in digital image processing, and that is principal component analysis, or in short we call as a PCA. And this is if you think that you are having two bands here, I am taking say example of band 1 and band 2. When I create a scatter plot, then what I see that how when in this plot I can assess that how these two bands are correlated. So what I find that they are highly correlated in this one, but I do not want to use for these two bands for further analysis, because if two bands are highly correlated, then no use of using even in false color composite or any other analysis. We are looking the bands which are less correlated or not correlated at all. So if this is the situation, then I want to use the maximum variations which is available along this direction. So this is what it is done here, that these axes are rotated. So in this x and y axes are rotated, and this becomes basically the origin also shifted. So the maximum variance which are available will go as a principal component 1, and then next variations will go in PC2. Think that if I involve 3 bands, then I can have a 3D plot. So there will be another one which will be perpendicular to this screen, and that will be also having variations, maybe little less. So that might become my principal component 3, and likewise then I can emphasize or use these variations and can create again color composites as well. So because of band correlations, what one see in band 1 is not so much different what one see in the band 2. As per linear algebra, we are making eigenvectors where eigenvalues contain the contribution of each band to principal components. As I have explained, that origin is shifted, the axes are shifted, and you get principal component 1, 2 and 3. This is a statistical technique which we can perform. So 6 principal components for band 1 to 5 and 7 for a Landsat image is shown here, and that this is 1, 2, 3, 4, 5 and 6. 6 is having a lot of noise, 4 is also having some stripping issues. Nonetheless, if I involve these principal components, then what you will realize that principal component 1 is having the maximum variations, and a lot of information can be derived further, can be derived from principal component 1, and whereas this principal component 6th, which is having only mainly noise. So up to 3 principal component 1, 2 and 3 can further used to create a color composite, and that will give you a really good information out of all 6 bands which were involved to create all this. So 6 bands through principal component analysis have been reduced to 3, and then all the variants which were available in different bands, among different bands, have come into the 3 components, component 1, 2 and 3. And then in later on, as you go further and further, you mainly get the noise. So noise has also been reduced or removed roughly, and then you get 3 components. All 3 components are completely different of the same area. So likewise, if we see here in a statistical means for all band 6 are here, and then there is correlation and covariance matrix eigenvectors can also be assessed here. When you compare band 1, of course it is going to be 1, and then you see that band 1 and band 2 are highly correlated. But so likewise you get a statistics as well, through which also you can assess about individual bands, among bands, and their statistics as well. So similar kind of tables can be created. Now there is one more step in this one. Instead of just creating a color composites, if we perform one more thing, like making a stretching over individual components, and that is this, if we do it, then this technique is called decorrelation stretch. So see, this example is that 2 bands are plotted here through a scatter plot, band 1 and band 2. It seems they are highly correlated, whereas compared to this band 4 and band 7, if they are plotted completely different bands, they are showing much more variation as compared to band 1 and 2, and in between band 3 and 5 are also showing some variation. So what we can do, when we shift the origin and axis, same time we can stretch these regions and can create more contrast in the images. So in most of the images, the radiation what you receive in one wavelength is strongly correlated radiation amount in most other bands. The best example here, band and 2, they are which are highly correlated. The bright is bright across the spectrum and end is dark. So we see color or spectral differentiation in infrared when radiation varies from correlation line. So band correlation produces images without much contrast. To eliminate a pastel colored images, we remove the correlation, and then we play in this color space. This is hue saturation intensity or hue intensity saturation or cyan magenta yellow color space, and we remove this correlation by stretching individual components, and by which ultimately in a color composite of de-stretched or stretched principal component, we get a altogether different output, and which technique is called decorrelation stretch. So this is how it is done. Then when then in a original RGB space, different bands are having correlated things, but when after decorrelation stretch, that is DCS, in the same color space, it is now occupying a complete cube. And if we play further in color space, we can send and can create more decorrelation among this. So this is how the color space can be exploited to create much better results, and this is the example here in the real image. This is the original false color composite which was subjected to decorrelation. So first the principal components means that means there were input bands were only 3, and the correlation among these 3 bands were determined, and then principal component analysis was performed. All 3 components came, and then using these principal components, they were stretched individually, and you go back again and put them in same, maybe in the same color scheme. So what do you find? That now you can differentiate this red with that red. In RGB, in simple false color composite, both are looking red, but here they are looking completely different. So decorrelation stretch will bring more colors basically into your image. That means completely less correlation. or roughly no correlation, and therefore more colors are there, and you may get an image which is easy to interpret, easy to discriminate between two adjacent objects as in this example, and can become very, very useful. So likewise, multivariate single channel or single variant or multivariate analysis can be performed using one band in case of simple spatial filtering, or involving multiple bands like in band ratioing, NDVI, principal component analysis, and decorrelation stretch. So NDVI and decorrelation analysis are basically offshoots of two basic techniques. One is the band ratioing, another one is principal component. The main purpose of digital image processing is to make image more clear than the original one, to improve the image quality. Why to improve image quality? So that my image interpretations becomes much easier and more accurate. If I go and perform classification, then my classification accuracy should also improve. So that is the purpose of digital image processing, to improve original image to an extent that image interpretations becomes much easier. Two adjacent features or objects which are present, normally they are not distinguishable through normal normal visualization, but if I subject these channels, bands, to like decorrelation stretch, then I should be able to see very clearly that how these two features are present. So I should be able to mark them, map them, and make my interpretation more reliable. So thank you very much.